Indeed. So every time we are starting, just remind me that you can start. Start. I should start recording.
Okay, thanks.
Yeah.
Because in the other one, we delayed by almost 20 minutes to record.
Oh, okay. Okay.
But we reminded the doc, but the started of ours.
Oh, okay. Okay. So but effectively, what I
Yeah.
can do, I think I can just put it on auto. Once I just start the session, I have it will start recording. But just remind me so that I check that it's recording.
Okay, no problem.
Okay. So this
Yeah.
course has four chapters or 4 units.
Yes.
Yeah.
Yes.
We'll go through them one by one. So the first one is introduction to soil and soil degradation. Then we'll look at soil
Yes.
conservation. Then we'll move to water conservation. Then in the end, we'll look at social and economic considerations of soil and water conservation.
Okay.
Yeah, so for today, we'll start with introduction to soil and soil degradation.
Okay.
Yeah. So if there are any questions, you can just interrupt and then we'll explain.
No problem.
Okay.
Yeah.
So basically at the end of this chapter or unit, you should be able to define what a soil is, its composition,
Yes.
and the
Yes.
functions. Then also
Yes.
be able to explain the different soil degradation processes and how they affect the performance of soil.
Okay.
Yes. So to
All
start
right.
with,
So, Mr. Miti,
yes.
uh, this PowerPoint, when I log on the recorded one, I'll be able to view them, right?
Yes, so it will be like this. The whole lot of this session is being recorded.
Oh,
So
okay.
what we are saying will
Okay.
just be you'll be seeing the PowerPoint, including
Okay.
what we are saying.
Uh, no problem. That's better then.
Okay.
Yeah.
So the first question that to ask ourselves is what is soil and what are its
Mhm.
functions?
Yes.
Yeah. So in layman's term, uh, soil is just a loose material that's found on the uh, upper surface of the earth, and it consists
Mm-hmm.
of the solid phase, the gaseous phase, and the liquid
Mm-hmm.
phase.
Mm-hmm.
So when you look at the composition itself, when you go into
Mm-hmm.
detail, you find that when you look at the soil, you're able to see the soil itself, like the brown material that we're able to see. So
Yes.
that material is mainly the mineral matter. So it's
Mm-hmm.
composed of the structural makeup of the soil, what we're able to see with our naked eyes. So that makes up the
Mm-hmm.
mineral matter, and it makes up about 45% of the soil. And,
Okay. Yeah.
yeah, so this is what we see when we talk of soil texture or soil structure. We mean this mineral composition. So if we talk of clay, silt, sand, this is what we are talking about, the mineral composition. So it accounts for about 45%.
Okay.
Yes. Then organic matter, that's the second component of the soil. So this can be
Yes.
living or non-living. So the
Yes.
non-living is the humus and maybe the leaves which are incorporated in the soil.
Yes.
Yeah, then you have now what we call the living component of organic matter, which are the earthworms, the microorganisms, and yeah, those things. So together, the organic matter will make up about 5%.
Okay.
Yeah, so it will vary. Like here in the tropics, organic matter is only about when you get about 2%, 3%. That's the normal range. But we can take it up to 5% as a general uh, 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 quantity in most soils. It doesn't go beyond that.
Okay.
Yeah. Then the other part consists of water and air. So 50%
Yes.
of the soil is air and water. Now these
Mm.
two would be antagonistic. If the,
Mhm.
the water increases, the air will reduce because
Mhm.
these because these two are found in the pore spaces of the soil. So as you
Yes.
increase this one will reduce.
Okay.
Yeah, and we know water is used by microorganisms to do
Mhm.
carry out their processes, and also the plants themselves, they use water to uh, uh, for their processes to take up nutrients and things like that. Then the air is what is used for
Mhm.
respiration of plants as well as microorganisms. So when we're talking of this course, these two
Mhm.
are the two major things that we want to look at: the water
Mhm.
and the air. So we want to
Mhm.
balance to say, okay, do we have enough water in our soil? So we will make.
Mhm.
So that's how come we're talking of water conservation. Then do we have
Okay.
enough air in our soil? That's how come now we're talking of
Yes.
soil conservation.
So conservation.
Yes,
Okay.
we want to look at these two parameters.
Okay.
Yes. So basically, this is what I was explaining. That
Yes.
just just a minute.
No problem.
Fabian, Fabian, hello, Fabian. When in class, is up to me. Yes, sorry about that.
No, no, no problem.
Okay. So
Yeah.
as sustainable soil and water management managers, we need to
Yes.
make sure that the water and the air are balanced.
Yes.
So meaning that we need to quantify these two properties.
Yes.
Yeah, so we need to say, okay, the amount of water in this soil is this much, or the amount of
Mhm.
air in this soil is this much. So in
Mhm.
quantifying them, we can quantify them in two ways. We can either use volume or we can
Yes.
use mass, or
Okay.
we can use properties which relate both.
Mhm.
Yes. So if we look at the soil, we said it's composed of the gas, which is the air, then there's the liquid,
Yes.
which is the water, then the solid is made up of the inorganic, that's the mineral matter, as well as the organic matter.
Yes.
Yes. So if you look at this diagram, it has differentiated those four components. You
Mm.
have the gas. So if you have a soil, they've taken a certain volume of soil, like this one,
Yes.
and then
Mm.
they've demarcated the four components. But of course,
Yes.
in nature, these ones are mixed, like they're intermingled. So, but this is
Yes.
just to show us how they are distributed. So in terms of
Okay.
volume, like this cube, we can be able to measure the volume of gas which it occupies, the volume of liquid which it occupies, the volume of
Mhm.
organic matter, and the volume of inorganic matter.
Okay.
Yeah, as well as their masses. But of
Okay.
course, when we're talking of mass, the mass for the gas is usually negligible. So we don't usually
Mhm.
consider it for when we're talking of mass. Yeah.
Okay.
Yeah. So if we take a look at these formulas here,
Mm.
the first one is just telling us that for a soil, if we get a particular soil, the total
Mm.
volume will be equal to the volume of air, the
Mm.
volume of the liquid, and the volume of the solid. So that would be the total volume. But you remember we said that as we are mostly interested in the volume of the water and the volume of air. Want to get that one right. So we introduce a property which we call porosity, which is a ratio of the volume of air plus water, the total volume. So what's the ratio of this volume of pores? So you notice that if you add the volume of pores and the volume of water and the volume of air, it will be equal to the total pores in your soil. So that's why we're calling it porosity.
Porosity, okay.
Yes. So in this porosity, that's if in this fraction of porosity, that's why you have water and air. So if one increases, the other one reduces. So porosity will be one parameter that is very important in our discussion or in this course till the end. So it's just the volume of pore spaces in the soil, and these pore spaces is where water and air are found. Yes. So if we're talking of porosity, it is the ratio of this volume of air plus the volume of liquid over the total volume of the soil. So in short, we'll be saying that our porosity is maybe 0.4, meaning that it's 40% of the total volume of soil. Or 0.3, meaning that it's 30% of the total volume of soil.
Yes.
Yes. Such that we can say that porosity plus this volume of solid.
Yes.
Okay. So it means that one minus porosity is equal to the volume of the solid phase.
Oh, yeah.
Yeah. So I think, yeah, this is just because this, when you add porosity plus the ratio of the solid to the total volume, the answer should be 1.
Okay.
Yeah, so you can be able to manipulate the two.
Okay.
Yeah, so that's about the volume. So volume will relate mostly to will relate it to the porosity. Then for mass, again, the total mass of everything, the components, is equals to the mass of the air, mass of the liquid, and mass of the solid. Yes. Okay. So for mass, we usually use two parameters. For if we're talking of the mass of the solid phase, because the solid phase, it's usually difficult to quantify it in terms of volume. So yes, in real life, the solid phase will be quantifying it in terms of mass, but the liquid and the gas will quantify it in terms of volume. Yeah, so for the solid phase, there are two parameters that we usually use. We use particle density and bulk density.
Density, okay.
Yes, so for the particle density,
yes,
this one which is given as PS, we get the mass of the soil.
Okay.
No, the mass of the solid phase of the soil.
Mass of solid phase, yes.
Divided by the volume of the solid phase.
Okay.
Okay. So it's the mass of the soil of the mass of the solid phase of the soil divided by the volume of the solid phase of soil. That's the particle density. Then the bulk density now is the mass of the solid phase divided by the total volume.
Okay.
So the difference is between Here it's the volume of the solid phase. Here is the volume of the total soil.
Oh, okay.
Yes. So
Uh,
these two parameters, we can use them to now combine, because we said porosity is the volume, right?
yes.
Now want to relate the mass of the soil and the volume of water and air, which is the porosity.
Yes.
So these two can be combined using this formula here, where we say the porosity of the soil is equal to
Yes.
1 minus the bulk density of the soil
Density.
divided by the particle density.
Particle density. Okay.
Yes. So
Mm.
in the module, we have an explanation of how this relationship comes about. So tomorrow,
Oh, yes.
when we are starting the lesson, we'll look at a few calculations, just going through. So this will
Okay.
be one of them,
Okay.
showing that porosity is equal to bulk 1 minus bulk density over.
Bulk density. Particle density.
Yes. So there are two ways.
Okay.
There are two ways in which we can measure porosity. First is just finding the volume of pores divided by the total volume.
Volume.
Or
Okay.
we can use this formula if we have the bulk density.
Density. Okay.
Yes.
Okay. All right.
Okay. So, but we'll look at these examples tomorrow as we start.
Okay.
Yes. Now we can look at the liquid phase of the soil, because when we start looking at water conservation, we need now to quantify the amount of water in the soil. Yeah, so there are two ways in which we can quantify water. Like we said in the previous one, we can use mass or we can use volume.
Yeah.
So because in the field, what we do is that we go to the field,
Yes.
we get the soil, then we weigh it.
Yes.
We weigh it, then we put it in the oven, and then after 24 hours, we weigh it again. So when you put it in the oven, the water will be dried, such that when we weigh it again, the mass will reduce. So the difference in the two masses accounts for the mass of water.
Okay, the wet and the dry soil.
Yes, the weight of the wet soil minus the dry soil, because when it's wet, we weigh it, then we dry it.
Yes.
Then we weigh it again. So meaning that the difference in the weight will be the weight of the water.
Okay.
Yes. So there's a parameter which we use, which we call gravimetric water content, which is the mass of water divided by the mass of dry soil.
Okay.
So mass of water divided by mass of dry soil gives you the gravimetric water content, which is this one. So to get the mass of water, we say it's the mass of the wet soil minus the mass of the dry soil.
Yes.
Yeah. So this is the gravimetric water content. So this is what we do when we measure the water in the field. So we just get a certain mass of soil. So we are dividing by the mass of soil. We want to relate it, because when you go to the field, you just get a small sample. Okay?
Yes.
So when we use that sample, then we calculate the gravimetric moisture content. Our answer is going to be certain grams of water per certain grams of soil.
Okay.
Such that if now we have a big field, we'll just estimate the mass of that soil, which will now help us to estimate the amount of water in that soil.
Okay.
Yes. So we have now with that we have this gravimetric moisture content. It's
Yes.
usually it's now difficult for us to estimate anything from it. For example, like Kuzambia sugar.
Yes.
When you're irrigating, you say we have irrigated how many millimeters of water, or
Yeah.
you use volume basis.
Yes.
Or if there was rainfall, we say there was 10 millimeters of rainfall.
Rainfall, yes.
So now what we want to do is that this gravimetric water content does not give enough information. So what we do, want to use volume basis. So the other measure will be volumetric moisture content, which now is the ratio of the volume of water in the soil to the volume
Yes.
of the total soil. So it's just the ratio. If we have this amount of soil, how much water is in it? So we just get
Yes.
that ratio. But this volumetric moisture content is difficult to measure in the field because when you go into the field, it's difficult to measure the volume of water.
Yeah.
So what we do is at first we calculate the gravimetric moisture content because that one is easy because we just weigh the wet soil and the dry soil.
Yes.
But now we want to convert it to volumetric moisture content. So in that case, we just multiply the gravimetric moisture content by the bulk density.
Okay.
Yes. So you notice here that it's saying volumetric moisture content is equal to gravimetric moisture content multiplied by bulk density over the density
of water.
Yeah, but the density of water is 1. So usually we don't even put it here.
Oh, yes.
Yeah, so it's usually gravimetric moisture content times bulk density.
Bulk density, okay.
Yeah, so again, tomorrow as we start, we'll go through to see how this relationship was derived.
Okay.
Yeah, why gravimetric moisture content by bulk density will give you volumetric moisture content.
Volumetric, okay.
Yes. Then again, like I said, this one volumetric moisture content here will be in volume units. That is, it will be in, for example, centimeter cubic over centimeter cubic. But like I said, when irrigating and when we are measuring rainfall, we use depth.
Yes.
We just say 10 millimeters of water has been irrigated. So want to reduce this volumetric water content to depth.
Yes.
But it's the same thing because when you look at this one, we say volume of water over total volume of soil.
Also, yes.
This volume is the depth of water times the area will give you the volume. Even this one, it will be depth of soil multiplied by the area. But since the area is the same, it means that we can cancel the area and the volumetric moisture content will still remain depth of water over depth of soil.
Depth of soil, okay.
So meaning that if I calculate volumetric moisture content in centimeter cubic per centimeter cubic, the answer will be the same when I calculate volumetric moisture content as depth of water over depth of soil.
Okay.
So if you're given volumetric moisture content, it says it's just the same as saying depth of water over depth of soil. Or if you want, you can say volume of water over volume of soil. The answer will be the same.
Okay.
Yes. just an example of volumetric moisture content.
Content, yes.
Yeah, if it is reported that the soil has a volumetric moisture content of 0.3 centimeter cubic per centimeter cubic,
Yes.
then they ask to calculate the depth of water in a soil that is 30 centimeters deep. So what this means is that they're telling us that for every centimeter of soil, you have 0.3 centimeters of water.
Of water, yes.
Yes, so that's what this one.
Okay. Oh, yeah, yeah.
Yes. So if they tell us that we have 30 centimeters of soil, for us to get the depth of water, we just simply multiply this ratio by the depth of
30
soil.
Yes.
So in this case, we're good. When we multiply the two, we'll have 0.9 centimeters of water. So mean that in that centimeter, 30 centimeter depth, 0.9 centimeters is water.
Okay.
Yes, so that's how now you can convert a volumetric moisture content in terms of depth, such that if, for example, they tell you that at Zambia Sugar, for example, that the amount of the volumetric moisture content in our soil should be, for example, 1 centimeter per 30 centimeters of soil. Okay.
Oh.
Then you do your measurement, you get your sample, you find that it's 0.3.
Yes.
So now you calculate it based on depth, and then you find that it's 0.9. So it means that the amount that you have to irrigate should be 0.1. So that that 0.9 plus 0.1 should be equal to 1.
1. Okay.
So that's why we're quantifying the volume of water so that we know how much water to add.
Okay.
Yes.
Okay. All right.
Yes. So, but apart from using this method where you go to the field and you sample the soil,
yes,
there are other gadgets which have been developed, which you just put in the fields. They are sensors per se. So they'll be, you just place them in the soil, then they are able to estimate the volumetric moisture content in the soil.
Okay.
So you don't have to go and get the soil and then take it to the oven and then weigh. So you just put it in the soil. For example, this one is what we call a neutron probe. So you just put pipes in the field at strategic points. So you just go with it and then you insert it in that pipe. So basically what it does, it sends out neutrons into the soil. So it sends them out to a radius of 30 centimeters, then they're supposed to come back. So if the soil has a lot of water, as they are being emitted, they're going out at a higher speed. But if there's a lot of water, their speed will be reduced.
Okay.
So what you do now is that you use a relationship between speed and water content to estimate how much water is there.
Okay.
So the slower the speed, the more water is there in the soil.
Okay.
So that's the principle how it works.
Okay.
Then there's yes. Yeah, the question.
No, I was just taking note of the point where you said the slower the speed, the more the water that is there in the soil.
Yes. So actually, what you can do now is that you can create an equation, a simple linear equation to say where you have water content and speed. So the water content will be like your y, and then your speed will be like your x. in a,
Okay.
in a linear equation. So if, for example, if the speed is high, means that the water content is low. So because
Okay.
now they will just go at fast, they are not obstructed by any water.
Yes.
Yeah,
That's good. Okay.
yeah.
Mm.
Then for the time, this TDR, it's a time domain refractometry.
Okay.
Yes. So for it, it works similar principle, but for it now it uses time. So
Okay.
it sends out electrons, an electric pulse into the soil. So
Mm.
if there's a lot of water in the soil, it will be the speed, like we said, will be reduced. So it will take a lot of time for it to go and then come back.
Okay.
Yes. So the more time it takes, then you know that okay, there's
There's
more
more water in the
more
soil.
water in the soil. But if it goes and then
Okay.
comes back fast, then you know that there's less amount of water in the soil.
All right.
Yes. So these are the two methods that you can use, which are not destructive per se, because the other ones, every time you go to the field, you have to dig some soil. So like you are now
Yeah.
you are destroying your field.
Yes.
But for these ones, you just put it once and then you forget about getting actual soil samples.
Okay.
But for this one, what you do is that you get a reading initially when you're setting it up.
Yes.
You get a reading of this machine. For example, the like this one, the time domain. You go to the field,
Mm.
you measure, you take the time it takes for the work for the signal to be read, for the pulse to
Yes.
go and come back. So, for example, you find that it's usually it's in milliseconds. For example, if it's
Oh, milliseconds. Okay.
0.2 milliseconds, for example, then you
Mm.
get a sample of soil and then you take it to the field, to the lab, you dry it, you weigh it, you get the gravimetric moisture content. Okay.
Mm.
Now you go, you relate it now that you say, okay, if my time was 2 milliseconds, it means that my gravimetric moisture content is this, which you calculated in the lab.
Okay.
Yeah. Then from these ones now, you create a linear equation,
Mm.
which now, when you go maybe after some time, you just measure this instrument, and then you say, okay, if 0.2 milliseconds is equal to this amount of water, what about this millisecond? How much water is it going to contain?
Okay.
So you just do that relationship. Then
All right.
means that every time you go to the field now, you don't have to sample the soil.
Okay.
Yes.
Okay.
Yeah. Then we need to talk about the status of water in the soil.
Okay.
Uh, so basically, we're talking about the energy with which water is held uh, uh, in the soil.
Okay.
So you notice that when you have a soil, when you start to add water to a dry soil, the water won't start to drain. For example, if it's in a flower pot, for example,
Mm.
add a small amount of soil of water, that water won't drain out
Mm.
until when you add a lot of water, you notice that it will start now coming out of the flower pot.
Yes.
When you're adding water to a dry soil, that water will be held by the soil particles.
Yes.
Okay, so that soil particles will have to exert a certain amount of energy to hold that water to the soil.
Okay.
So that amount of energy is what we call the matrix potential.
Okay.
Yeah, so it's usually measured in kilopascals or bars or centimeters. So
Potential.
yeah, what happens that if a soil is very dry, when you add water, it will have a higher affinity to hold that water. But as you continue to add water, that affinity will reduce because one, the soil particles, they have
Yes.
they have absorbed enough water, and as you add more water, the other amount of water will just be drained away because they have
Oh.
enough. It's like a person. If they are very hungry, the moment
Eat
you
more
give
food.
them food, they'll just be getting until they become full. The rest of
Yes.
even if you give them more food now, they will just say, ah, it's okay. So that's what happens. The particles will attract more water, more water, more water, and then the rest they'll start to release it. So
Okay.
this has a consequence in water conservation. So
Okay.
what we want, because when we start to irrigate, as we start to irrigate, the water will be held by the soil particles. Then
Yes.
as you continue to irrigate, it will reach a point where now the soil particles have attracted enough water, and the other water that you're adding will simply just be go to waste because it will just be draining out of the soil.
Yes.
So your task as a soil conservation manager is to know at what matrix potential does the soil is the soil like saturated? At what potential does it now start to let go of this water? So at that potential, that's when you stop to irrigate, because the more you irrigate, you're just wasting the water.
Yes.
So that's why now we are interested in this matrix potential of the soil.
Okay.
Yes. So at this stage where the water starts to drain, it means that the soil particles have absorbed enough water, and the pore spaces as well, the pore spaces of the soil have enough water. They have held enough water. So the rest are just being left to waste. So that's why we need this point of to know the amount of matrix potential in the soil.
Okay.
Yeah. So this matrix potential is usually measured using different gadgets as well. So you just place it into the soil. Then once you place it in the soil, depending on the dryness of the soil, it will give you a reading of the matrix potential.
Okay.
Yeah. So as you irrigate, that potential will start to change. It's moving from being more negative to being more positive.
Okay. All right. I'm trying to think how we can use this here.
As in where?
Like in our fields.
Okay, in your fields. Yeah.
Yes.
Yeah. So what
how can we set it up and just is it to automate it or something, or we have to physically every time check?
You can automate it because nowadays you have gadgets. So what you do is that you put it in the field.
Yes.
So you just place it into the soil. So it's measuring how dry your soil is based on it's measuring the matrix potential based on how dry the soil is. So as you start to irrigate, that matrix potential starts becoming more positive.
Yes. Yes.
So if you've automated your irrigation system and you've connected it with with your matrix potential sensor,
Yes.
means that it will be reading your matrix potential. As soon as it reaches a certain point, then your irrigation will switch off.
Okay.
Your
Yeah.
irrigation system will switch off automatically.
Okay.
So you can actually automate it.
All right.
Yes.
There are some things they call it, but moisture probes.
Yes. So you can actually use. So there are two things here.
Yes.
We can use moisture probes, like we said. The
Okay.
ones. So the ones we're talking about. These ones, the neutron probe or the TDR
Yes.
or the
Yes.
moisture probes we're talking about. They are
Yes.
different gadgets. So they use
Okay.
basically the same principle. So
Okay.
in terms of irrigation, you can
Yes.
place them in the field, just like
Yes.
and
Yeah. Because yeah.
you can automate them with your irrigation system,
Okay.
such that or what you can do, you can have them separate, and then you can monitor because, for example, the way we have at Unza Farm, we have
Yeah.
moisture probes, so they are
Oh.
giving readings every 15 minutes. So
Okay.
you can check to see, okay, now the moisture content has dropped to this level. So I need to start irrigating now. Then as you irrigate, you monitor the moisture content using the moisture probe, and then you switch the machines off if you reach a certain level of water.
Okay.
Yes. So, but we need to understand that there's depending on the soil that you have,
Yeah.
the amount of water which the plants can extract will be dependent on how tightly it's held on your soil particles.
Okay.
Which is why it will be more safe to use the matrix potential sensors than the volume than your moisture probes.
Okay.
Because if, for example, you can have a certain moisture content in the soil,
Yes.
of which, because we said that they are held by the soil particles. So
yes,
for the plants to extract them, the plants have to use energy to detach them from the soil. So different plants will have different capabilities. So
yes,
some plants will have higher capacity to extract than others. So even a certain moisture content, one plant can dry up in those conditions, while another one can survive because it has enough capacity to extract water from the soil particles, while the other does not have.
Okay.
Yeah, so we need to monitor this property, the matrix.
Okay.
Yeah, the matrix potential.
Potential. Okay.
Yes. So in dealing with matrix potential, there are usually 2 points which we usually consider. So there's the permanent rooting point, okay, what we call the field capacity.
Okay.
When we say permanent rooting point, we mean that it's a permanent rooting point is the water content at which the soil is going to hold on tightly water in the soil,
Okay.
such that a plant cannot extract it from the soil particles.
Okay.
Meaning that that soil now will that plant will start to wilt because it doesn't have water.
Okay.
So the water will be there in the soil, but the plant cannot extract it because it needs a lot of energy to extract it.
Okay.
Yes. So now as we start adding water to the soil, it starts to move from permanent wilting point, starts to increase. Then that
Yes.
water, that extra water, the plant is able to extract it. Okay.
Yes.
So that water will still be in the soil, in the soil, in the soil. Then it will reach a certain point where now this water has become a lot, and
Mm.
as you add, that water will just start draining by gravity. It will start draining to lower depths.
Yeah.
So at that point, when now the soil has become has had enough water that
Mm.
the X amount of water that you put starts to drain out is what we
Mm.
call the field capacity.
Capacity. Okay.
Yeah, field capacity. So basically, what we want is that we want our water content to be between permanent wilting point and field capacity.
Okay.
So you don't want it to go below permanent wilting point because your plants cannot extract it. But
Okay.
you also don't want it to go above field capacity because as you add, the water will just be draining out.
Draining out. Yeah.
So you as the field manager, you need to maintain your water levels between these two.
Permanent wilting point and field capacity. Yeah.
Yes. So
Okay.
so what happens will be this. Let's say that we start from a dry soil.
Yes.
You are going to make you've measured your matrix potential at permanent wilting point. So you start to irrigate, you reach field capacity, then you say, okay, now because the extra water that I'm putting will be wasted, you stop.
Mm. Mm.
Then the plants will start to use the water. So you start to monitor it.
Yeah.
It will start dropping.
Yes.
Dropping. When it reaches permanent wilting point again,
You start applying what?
you start applying water, such that
Okay. Yeah.
you have a cycle. You have a
Yes.
cycle. For example, when you irrigate in the morning today, for the water
Yes.
to dry to go to wilting point, maybe to take 3 days.
Yes.
So meaning that your irrigation interval will be every after 3 days.
3 days, yes. That's a
Yeah.
cycle, yes, interval. Yeah.
Yeah. So you use this information to come up with such regimes of irrigation.
Okay.
Yeah. So, but when we say there's this property which you say available water. So this available water is
Yes.
just basically the amount of water that is available to the plant. And this
Okay.
one will be the difference between field capacity and wilting point.
Okay.
So it means that the water that is between field capacity and wilting point is the one which is available for the plants to use.
Okay.
Below that, they won't use it because it's held by the soil particles.
Yes.
Above that, it will be draining
Draining, yeah.
to groundwater. So available water is within those two parameters.
Okay.
Yeah.
There's a software we are using here
Mm-hmm.
with a similar principle. We call it KenPro.
KenPro?
Yes, it's a KenPro. Anyway, it's specific to Nakambala.
Okay.
It's a computer software.
Okay.
But the principle is the same.
Mm-hmm.
So what we've done is we've established each field.
Mm-hmm.
like what is we call it the TAM, total available moisture,
Yeah. Mhm.
through these soil laboratory tests.
Yeah. Yeah.
So we know to say field A, for
Mhm.
it to reach field capacity
Yes.
or total available moisture, it's at maybe, let's say it's 90
Mm-hmm.
millimeters of water or so.
Yeah.
Then we say, okay, to at what point are we going to be irrigating? Mostly we use about 50%.
Yeah.
So we say at 45,
Mm-hmm.
I need to put water because 45 is 50% of 90. If a soil has got, let's say 90%.
Mm-hmm.
So mostly when we apply water, so it works on assumption that ukapaka it goes to the field capacity.
Yes.
Then you start monitoring your graph based on the evapotranspiration. Also, we factor it
Yeah.
in.
Yeah.
Then the moment you see that your graph is almost hitting your 50%,
Mm-hmm.
you apply the water.
Yeah. Yeah. Yeah.
You take
So
it back again to the 90. So it's almost a
yeah.
similar principle.
Yeah. So basically,
Mhm.
why you're going to 40, because the
Yes,
total available water is 90, right? But you're going
yes, yes.
up to 40.
Yes,
Uh,
about 40, 45. Yes, we assume at 50%,
yes. So the idea
we
there is
must
that
put the water.
yes. So the
Yeah.
idea there is that
Mhm.
you are not letting it to reach zero,
The
because
permanent routing point.
yes,
Yes.
because effectively what happens that when it reaches permanent tilting point, for you to start now absorbing again that water, the plant would have become weak.
Yeah.
So you don't want it to reach its lower limit. So you just make
Yeah.
sure that okay, you know that okay, this is the lower limit, but you just make sure that
Yes.
above, you use something which is above before
Yes.
it.
Yes.
Yes. So
Yeah.
it's like you don't want to become very hungry.
Yes.
So
Yes.
such that okay, now you know okay, when you start feeling hungry, you top up with something, because when you become very hungry, maybe you start feeling dizzy, and then
Namausa as well.
na mouse. So you want it not
Yes.
kunkala like to be very dry.
Yes.
Yeah. So that's good. That's a good application. Yeah. But
Okay.
it's
Then we also use augers.
mhm. Yeah. So my augers, it's basically data to come
Mhm.
up where you get the soil, then you go and they take it to the lab, isn't it?
Yes. So yes, we also use an auger. You see, okay, how wet is at what point? Where is the dry point? Is it at 10, 15?
Oh,
Then you
okay.
also, yeah, it can also guide you to say, okay,
Mm-hmm.
this soil still has water, or we need to apply water in this soil.
Okay. Yeah.
Yeah.
Mm-hmm. Yeah. So basically, the ones for augers, because those ones you don't usually do them on a regular basis, because of course
Yes.
it will be costly and it will be laborious.
Yes.
So
Yes, for sure.
usually those ones are used to monitor if your sensors are working properly. So
Yeah.
you want to compare, say, okay, is the sensor telling us the right thing?
Uh-huh.
Yeah.
Yes. You're
Yeah.
just verifying to see if information is correct.
Yeah.
Yeah.
But basically,
Okay.
when you have the sensors, it becomes easier to automate things.
Okay.
Yeah, yeah. It's good that you see these things in practice. It's easy to relate. Yeah. So okay, we're talking about okay, volume. Okay. So for
Okay.
yeah, for these two
Yeah.
for these two parameters, the fluid capacity and the working point, you can use what we call a moisture characteristic curve to determine the volumetric moisture content at different matrix potentials. But what we realize is that for different soil textures, the amount of water held at a given matrix potential will. Okay, sorry, I'd lost connection. Hello? Hello?
Yeah. Yeah. They're in the connection.
Oh, okay. I think Nico, no, it had lost internet.
Oh, okay. All right.
Yeah, yeah. So I was saying
Okay.
that the matrix potential and water content can be related to
Yes.
what we call soil moisture characteristic curve. So this just
Yes.
shows the relationship between the moisture content and the matrix potential. So
Okay.
if you have a certain matrix potential, what is the volumetric moisture content? So you relate
Yes.
to say, okay, if your permanent melting point is at a certain volumetric moisture content, then you know that, okay, if I reach this matrix potential, it means that my water content has dropped to this value.
Yeah.
Yeah, so you realize that different textures have different curves. So for
Yes.
a given matrix potential, you find that maybe a a clay soil will hold more water than a sandy soil.
Yes.
Yeah, so you can use this depending on your soil So
Okay.
yeah, the gadgets that you put in the field, you can relate them to these curves.
All right.
Yeah. Then I hope it's still recording. Let me just check.
Yeah, I can see it here.
Oh, okay, okay, all right.
I
Yeah,
think it's recording.
okay. So as we are going to I think we just have about 2 or 3 more slides to go. So
Okay.
yeah, the other way that you can uh, uh, estimate this property, the working point and the fluid capacity, is through what we
Yes.
call pedotransfer functions. I don't know if you
Okay.
I don't know if you've heard of them, but
No, this one, it's
yeah,
the first time.
yeah. But so these ones usually they're used when you are mostly in research purposes, where like
Oh, okay.
for example, because doing a measuring the moisture characteristic curve, it can take
Yes.
you about 3 months to come up with the whole curve. So it's
Mm,
usually difficult to do that. For example, if like for example Zambia Sugar, they can do it because they have the capacity. But
yeah.
if it's a normal farmer, just a small
Yeah.
farmer, it's difficult. But
Yeah.
usually these farmers have measurements maybe for soil texture.
Yeah.
So what pedotransfer functions do is that they estimate the this working point and fluid capacity based on certain
Mm,
easily measurable properties, for example, clay content or sand content.
yes.
So
Yes.
if you know the sand content, you can be able to estimate your fluid capacity and your working point.
Okay.
Yeah, so these functions, there are a lot of functions that have been developed for different areas, maybe Europe, Zambia, Africa, and different areas. So basically, these ones, you use a function that was developed in conditions that are similar to your area.
Oh, okay.
So you can't say, you can't get a function that was developed in, for example, in UK, and then use it
Mm,
for Zambian soils. It will give you
mm,
different result. But if you use something which was developed in Zambia, you use it
yes.
for your soils, then you know that okay, it estimates almost a similar amount.
Okay.
Yeah. So like for me, when I was doing my masters, I was evaluating
Yes.
different pedo transfer functions, how
Okay.
well they're able to estimate moisture content for our local soils. So because,
Oh, okay.
yeah, because for Zambia, uh, as of now, we don't have functions that are specific for our soils.
Oh, okay.
Yeah, so I was testing which ones estimate better our local soils.
Okay.
Yeah. So, but now in this project that we are working on,
Yes.
now we are developing functions based for Zambian soils. So these ones will
Okay.
be specific for Zambia.
For
So
Zambia. Oh,
yeah, so it's specific for Zambia, Malawi, and Zimbabwe. So we use,
okay.
yeah, we've used
Mm,
from these three countries.
yeah.
So basically here, there's an example here to say, okay, if you
Mm,
know the sand, clay, and silt content of the soil,
mm,
as well as the bulk density, then they're asking you
mm,
what is the available water. So
mm.
so usually field capacity is measured at 33 kilopascals.
Oh, okay. I
Yeah.
was going to ask to say why 33.
Oh yeah. So
Okay.
yeah, 33 simply because they've estimated, they were
Yeah.
measuring the potential in the soil, and they are measuring the drainage. So
Okay.
at the point when the soil starts to drain, they look at the potential and
Yes.
they found that it was 33.
Okay.
So but it's not an exact value, it's an estimate.
Okay.
Yeah. Then the same for rooting point is 1,500 kilopascal.
Yes.
So these two equations, now you're able to estimate if you have your sand content. For example, in this case, it's 30%. Yeah,
Mm.
30%. So you just place your 30% here, which will be 30 over 100 as a percentage.
Oh, okay.
Yeah, so it will be 0.
Oh, so the 0.413 is, oh, okay.
So this
Oh,
now is
because we're talking of sands. Oh,
yeah.
yes.
So here, when you put our sand content here, that is in this equation,
Yeah.
it will give us this amount. So this one is the volumetric moisture content.
Okay.
So it basically means that 40% of that soil is 40% of it is water.
Okay.
Yeah. Then for the field, for the rooting point as well, it has three variables. So you have the sand, silt, and bulk density. Just
Yes.
place the percentages of sand, clay, and then your bulk density, which is 1.5. Then to give you the volume of water at permanent rooting point. So
Okay.
now we have these two,
Yes.
0.4 and 0.2. And to find the
Yeah.
available water, we said that it's a difference between field capacity and
The
rooting.
permanent rooting point.
Yes.
Yes.
So you don't want your
Which is
volumetric,
0.2.
you don't want it to go below this one, and you don't want
Yeah.
it to go above uh, uh, that one.
Okay.
Yeah. So that's the principle. I think,
Okay.
yeah, I think this should be our second last slide. So this one basically is just to
Okay.
show how we can measure the matrix potential in the lab. I don't know if you have
Okay.
I don't know if you have this equipment at Zambia Sugar. for measuring the matrix?
No,
Oh, okay.
this one we don't have it.
Oh,
I would
okay.
love to see it. I hope I have an opportunity to come my research.
Yeah, we have them
Just
at UNZA.
Okay, just even to look at it, yeah.
Yeah, yeah. So the principle is that because we are saying that the water is held with a certain energy around the soil particles. So what we
Yes.
do is that we wet a soil,
Yes.
saturated. Then we put it into this chamber, like this one here. We put it here, here. Then we close.
Yes.
So basically, after we close, it becomes something like this. So we close here. Then we apply a certain pressure. So
Yeah.
that pressure will be equivalent to working point and field capacity. So in one chamber, we apply 33 kilopascals.
Yes.
So mean that when we apply this force here, the amount of water that is in these soil particles, because of this pressure, because this thing is closed, if you have this pressure, it will start to remove water from the soil.
Yes.
Draining it down here. So the higher the pressure, the more water will be draining.
Okay.
Meaning that when you apply a pressure of 33 kilopascals, less water will drain and you have more water left in your soil.
Okay.
Then when you apply 15,000 kilopascals,
yes,
more water will drain, such that the moisture content that you're going to measure in the end after this whole exercise, what you're going to refer to as your permanent wilting point.
Wilting point. Okay.
Yes, so you have two. One at 33 kilopascals, the amount of water that is going to remain in your soil is the field capacity. Then the amount of soil that is going to remain at 15 kilopascals is what is your wilting point.
Okay.
Yes. Yeah. So yeah, I think we can stop here for today.
Okay.
And we'll continue tomorrow. So tomorrow, basically, we'll look at
calculations.
We'll look at the calculations. Then, or what we'll do, we'll start with the because tomorrow we'll look at now the degradation, like what is degradation and things like that. And I think afterwards, that's when we'll look at the calculations. And we'll see which one will be best. But basically, what we've talked about relates to water. So it's we use these principles to conserve water. Then when we talk of degradation, we use those principles that we will learn in degradation to conserve soil.
Okay.
Yeah. So So I think for today we can stop here and then we'll continue tomorrow.
Okay.
Yes, but I like it because that's what you are doing and you are relating it to the actual practice. It's usually difficult for people who are just coming now, like they are from a totally different
field, mining.
So now you have to start explaining to the core what is, and now for them to relate, so it takes some explaining. But this, we are relating it to the field, which is very, very interesting.
Yes.
Yeah, and then maybe
because I've seen our class mulima teachers
environment
na mining.
Yeah.
Yeah,
Maybe
agri key,
that teacher of chemistry. So I find that
na geography one bit.
for you to explain such, and
Yeah,
for someone to picture it
yes.
becomes it becomes difficult. But it's 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 good that it's
Yeah,
moving on well.
yeah,
And
yeah,
you'll be able to apply it.
yes.
Yeah. Mm.
No, I think I'll be even better once we do the examples, Yama formulas. I went through alone
Mm.
just up to almost this point.
Oh, okay. Okay.
Eh,
Yeah.
nabele ngako chepa ngono chena ta, I think with explanations I'll be able
Yeah. Yeah. But
to relate on
yeah.
the density and all those things.
Yeah. I don't know how tired you are now.
Mm.
If I don't know if it's okay, we can still go through those relations if your brain is not yet saturated. But if it's saturated, then we can do it tomorrow.
Yeah, I think we do tomorrow. Yeah, kai kachoka muri
Yeah.
ya otashe.
Okay. Okay. I think then we can just sort it out tomorrow.
No problem.
Okay. Okay. No.
Yeah, appreciate at least yapa, yeah, it's better.
Yeah. 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 Mm,
Mm.
yeah.
Yeah.
And it would have been it's best like we do a lot of practical on this one, because this one
Yes.
is more of a practical course.
Yes.
So, but the software that you use at Zambia Sugar, do you use them as well, or there's someone, it's another department which uses them?
Like Ken Pro, I'm also using it.
Oken Pro. Okay. Okay. Okay.
So that one I'm using it. Then we've got my probes, my Oga, those at least I'm using them.
Okay. 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 Even better. Yeah.
Yeah.
So usually the softwares, there are some which are maybe ngakata Zambia Sugar ndiye wana right to it.
Like Ken Pro, ndiye mwana
Okay. Yeah.
it's actually owned by Irovo. It's specific to just the Irovo group.
Okay. Okay. Yeah.
Because
Yes.
Zambia Sugar, we are part of that Irovo group. So you find it in all the Irovo mills that
Okay.
are growing sugarcane.
Okay. Okay. But yeah, usually it's the same. They usually use the same principles, and you
Yes.
basically use almost the same type of inputs.
Yes. Yeah.
Yeah. But yeah, yeah. We can even also develop our own if
Yes.
if we have if we take enough time. So for
Yes, like
example,
the ones you've told me on the petrol, the one you're doing now. That's good. That relates
yeah,
to our souls.
yeah. But even just
Mm.
creating a software itself, it's it's, it's,
Yes.
it's these things are not they're not difficult.
Mm.
It's just a matter of understanding how the process occurs.
Yes.
Then you just
Mm.
model it, and then you have your program.
Then one can nama rights Wambuguris.
So there's a program here, the one I'm developing for land evaluation.
Oh, okay.
Yeah. So it's just it's still being built, but
Yes.
it's 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 something that you can do even for these things.
Yes.
Yeah, it's just a matter of understanding the process, and then maybe
Yes.
doing a bit of programming. Then it will be, you can do anything. That's why.
Yeah. Mm.
Yeah.
Okay.
Okay. So anyway, let's continue tomorrow. So
Yes, Mr. Meet, thanks.
yeah,
Yeah.
I don't know. We continue at the same time, or when you are free, you can just inform me. Then
Yes.
we can proceed.
Okay, no problem. I'll give you a call.
Okay, okay,
All
okay.
right.
All
Then
right.
on the research,
Mhm. Yes.
we can discuss tomorrow during the week.
Okay, okay. I think let's discuss tomorrow.
Okay,
With
all right.
yeah, we see because this project that we are doing, we do measurements for like I said, for moisture, for uh bulk density. Then we also do
Yes,
penetrometer measurements.
yes,
All those have to do with structure. So
yes.
yeah, so the idea now maybe is to I'm trying to think of a way of how we can relate it to the environment based on that site. Then
Okay.
then see if because Dr. Peer is the one who is the PI,
Oh, okay.
and then see if a student can be engaged on that project using that data. But because it's
Okay.
a yeah, but because it's a project, there are some conditions
Okay.
on how to use the data that is generated.
Okay.
Yeah, so but first when I try and see how we can use the data, then
Okay.
maybe the best is now we develop research questions. Then
Yes.
obviously because it's in that field, because for me now I'm not able to supervise a master's thesis.
Yes.
So
Okay.
what to happen? Obviously, if you go that route, it means that it's obviously going to be Dr. Piri. And
Okay.
and if it's Dr. Piri and you've
Yes.
already set out those research questions, then now
Yes.
you look at it and then see, okay, we have this field already which we're doing on this project. Then maybe he'll be able to throw you on that project.
Okay.
That's my line of thought.
Okay. All
Yeah,
right.
yeah. But anyway,
Okay.
let's discuss tomorrow to see.
Okay. No
Yeah,
problem.
yeah. See how we can do it.
Uh,
Yeah,
all right.
yeah,
Okay.
yeah. No,
All
thank
right.
you.
Thank you, Mr. Meet.
Okay, no, thank
Then
you.
my bundles, you're using a phone as well.
Uh, I've Nakula Kajaka Unlimited.
Oh, okay. All right.
So it can go on and on.
Okay. All right. Okay.
Yeah, yeah, yeah. Oh, now we are using bundles. Oh,
Oh, yeah. Kunyumba niba using actually my bundles, but it's fine.
oh, okay, okay. Then
Yeah, I use my phone and connect to the laptop.
maybe we can be doing it while we are at the office.
No, I know it's okay.
Oh, okay, okay.
Depending on the time, it's fine. Anywhere is okay. For office, niba using like the watershed, I use the office internet.
Oh, okay, okay, okay. So, but if
No, it's fine. Whatever time is okay with me.
oh, okay, okay. So, but
Eh,
if you have time in the afternoon or any other time, you
yes,
can just tell me. Then
yes,
we can just schedule while we are here at the office.
yeah. Especially when we don't have watershed, because watershed nama ilofutiri kumazuru. But if we don't have it, I would definitely be letting you know.
Oh, okay, okay, okay.
Eh,
Yeah. Then
so watershed we are 10.
oh, yeah, 10.
Napenda beze meeting na WhatsApp. So there are 10. Yeah, at least there are 10 students there.
Oh, okay, okay. Yeah,
Eh,
yeah. Then
mm,
what I would do for this video is that
yes.
I'll upload it to YouTube. Then I'll send you the link. So you can
Oh,
just
no problem.
follow the link to go to YouTube, because it's very big. For it to go per email, it will be,
Oh,
yeah, it
mm,
will be, yeah. So I'll
okay.
just send it via YouTube.
No problem.
Okay.
Thank
Okay,
you.
thanks.
Thanks a lot, Mr. Meet.
Okay, thanks.
Thank you. Have a good evening.
Good evening.